Momentum and Rotation Review 5. Initial and final velocity vectors are shown below. For each scenario, draw a vector to show the direction of the net force that must have acted. Here we have the initial velocity vector, and here's the final velocity, and we want to know something about what kind of force must have acted in order to change the velocity from that into that. So here's what I'm seeing. Initially, there's velocity in the x direction, and at the end, there isn't at all, which means there must have been a component of the force anyway that has acted that way to, in effect, cancel this out. What about the y component of the velocity? That hasn't changed, has it? It looks exactly the same at the end as it did at the beginning, which means the net force didn't act in the y direction. I think there's the direction of your net force for that one. Let's take the one to the right of that. Now, what happens here? Let's look at the x components of velocity. Initially, the x component looked like that to the left. Here, it's only half as much to the left, which means there must have been a net force vector that acted a little bit to the right to cancel out some of that x velocity. What about in the y direction? In the y direction, we've got 2 units of y velocity up, and here we got 3 units of y velocity up. So that must mean that the net force must also have acted in the y direction like that a bit. The net force is going to be the sum of these. So the net force is maybe going to look, kind of like that. Let's go back to the left here. Here we have an initial velocity and a final velocity. The y component has completely disappeared, which means we need a y component of the force that goes down like this. The force must have acted in that direction. And what about in the x direction? It was going 2 units to the right, and now it's going 2 units to the left. So we need to exert a force that much, you might say, to cancel out that Vx completely, and then again that much to give us that final velocity. So the net force is going to be looking like that. How about over here on the right? The initial velocity looks like that. There's no y velocity at the end, so the force must have acted downward quite a bit, but it also must have acted to the left just a touch, like that much maybe. And when we add those two together, the direction of our net force then must have been kind of like that. A couple more. What happens to the x velocity? It disappears. So our net force must have acted that way. What happened to our y velocity? It increased a bit, didn't it? Which means the net force must have acted a little bit like that. So I'm thinking that our overall net force might look kind of like that. Last one. The y velocity initially was nothing, and at the end it's that, which means that the net force must have acted like that. Initially, the x velocity looked like that, and at the end it's nothing. So our net force must have canceled that x velocity like so. I'm thinking that the net force had a direction kind of like that. Let's do one more in this video. 2 objects, not necessarily of equal mass, approach each other, collide, and bounce off. Determine object 2's final momentum. So here we go. These 2 are heading towards each other. We don't know what their masses are, but we do know their momenta. And so, is momentum conserved in this collision? Absolutely it is. So I think the momentum in the x direction, p in each direction, is conserved. So in the x direction, how much is the total momentum? We can do this in our head, can't we? 4 kilogram meters per second to the right. That's what we have initially. See, 7 that way and 3 in the opposite direction. So the total in the x direction is 4 to the right. Now look at our picture. Mass 1 doesn't have any x momentum at the end. That means mass 2 must have all of it. All 4 kilogram meters per second that way, mass 2 must have that in the x direction. What about in the y direction? In the y direction, how much momentum do we have initially? None. Which means at the end, how much total y momentum must we have? None. And if mass 1 has 3 going up, then mass 2 got to have 3 going down. So the final momentum of mass 2 is going to be 4 over and 3 down. 4 over, 3 down. What's that? 5. What's our final answer going to be? 5 kilogram meters per second at what angle is this? What do we know this to be? 37 degrees? 37 degrees below the positive x-axis. There are any number of ways we could describe that, but if the x-axis points positively to the right, we could say that.